online throughout the whole semester. So, right, so we're doing linear algebra. Not calculus at all. Not calculus. Actually, I have to say two things. One is that you'll see my facial hair get longer and longer. I'm actually entering a charity ear growing contest. I swear to you, it is true. It is not just an excuse. I'm trying to help raise a little money for autism education for children. And this is a good excuse not to show as well. So anyway, by the midterm it should be pretty scary. The next thing though, seriously, is calculus. Okay, so I haven't taught a non-calculus course before, for a long time at least. So this is going to be fun for me too, or at least fun for me. So here goes. Before I begin, are there any sort of general questions on people's minds at this point, just about the course, about the sessions, something?
Yeah, do you think it's smaller than yours? I feel like last year was
you mean is the course enrollment smaller? I don't know, there are quite a lot of sections of it, so I think there are maybe 9 or 10 sections. You should still be looking at the high 100s. I'm not sure if that's smaller, but I mean, there's fewer people here, but it's the first time. I'd imagine the night before the midterm, it'll be hard to get a seat. That's how it goes. Any other general questions? I can tell you that exam review sessions as well, so I'm not going to really be going ahead, and I know that the homework's sort of just being handed in, and it's like a long-term view. Okay, this is my whole approach. Is that, okay, the homework's important, but it's kind of good for you to struggle through it. It doesn't count for very much in terms of the final grade, but it is very useful to make sure you're keeping up. But I'm looking at the midterm, I'm looking at the quiz and the midterm and the final. So I'm just trying to consolidate this knowledge from the previous week. That's the philosophy. So rather than just do a quick fix to get you through the homework and then you forget all about it, like, I kind of want to just really reinforce these concepts and do a lot of examples. Now, seeing an example, I mean, last semester I did, there weren't too many brought in by you guys, and that's fine. If you bring in questions, well, if you have a question on something from the homework that wasn't clear to you, and that's ideal. That's ideal. If you ask me about next week's homework, I'm liable not to show you exactly how to do the problem, but we can give you some hints as well. So that's the general philosophy. So I tend to redo a lot of what you did in the lectures, but with more examples. Because I assume you've already seen the theory. This is not supposed to replace the regular classes either. I'm assuming that you've seen it before. Okay, so let's sort of dive in. So I'm going to try to cover all of chapter 1 and the first 2.1 and maybe 2.2. So it's just sort of bringing us up to where you are now in class. Different classes at different rates. But in any case, just in the way. Let's full case. I see that'll do. People can still get in. Right, so look, we're dealing here with matrices pretty much the whole course. So I might as well tell you what a matrix is, or remind you, of course you've seen them. Okay, so there's some confusion about n by m. If you say an n by n matrix, it's maybe not so intuitive that it should have n rows and n columns. And if you write the coefficients in a standard sort of way, then the top row goes A11, A12, up to A1m. There are n of these numbers, m of these numbers this way, and then A21, A31, and so on up to AN1. There are n of them that way. The reason I think this is a little parameter is if you think of this as the x coordinate and this is the y coordinate, it's wrong. That should be A21. So that's the point 2, 1. At least if this was going positive. But that's just not how it's done. I'm sorry. This is how it's done in linear algebra. So you just got to deal with it. And this goes all the way through to ANM. Now, this is a nice little formal construct. It's a very convenient thing, but what you really want to do is think of it as a coefficient matrix. So these are coefficients of equations. And most of the applications, at least at first, we sort of move into the more theoretical aspects of matrices, but not underlying this is the idea that these represent so-called linear combinations. This is moving, that term is not introduced until 2.1 or 2.2, but whatever. You've seen that now. What I'm thinking of is that the first row represents A11, X1 plus A12, X2, and so on, up to A1M, XM. That expression, where x1, x2, up to xm are variables. Now, of course, there's only a 3 by 3 matrix or something, but if m is 3, then you could use x, y, and z instead of x1, x2. But in general, we don't have letters of the alphabet that are obvious. Even if you started A, B, C, you'd quickly run out. Or at least if you're working in more than 26 dimensions, you'll run out. So, of course, you have to resort to these subscripts here. All right, so the first column, the first row, rather, I want you to think of as sort of mentally representing that. And there's a separate linear combination for each row. And so on, until you get to the last row. And you use up all the coefficients. So there's n different sort of linear combinations of these variables x1 through xn. Now, what you often want to do is say, oh, this equals something. This equals something. So what you would do in that case is if, for example, the first one equals d1, the second one equals d2, and so on, so the last one equals dn, there's n of these equations now, then what you would do is put a dotted line or sometimes a solid line, and you fill in these d1s, d2s, up to dn. And now this is called an augmented matrix. We've taken the coefficient matrix and augmented it by one column, which are not really coefficients, but are rather constants on the right side. Now, the reason, of course, this is called linear algebra is that these are linear equations. What is a linear equation? Well, basically, It's a generalization of a line. So a plane is like a line in 2 dimensions, or in 3 dimensions. It's a 2-dimensional line in 3 dimensions. And we'll see subspaces soon enough, and these are sort of the general idea. So these are linear equations, and it's worth understanding the geometry of what can happen. So because we cannot think in n dimensions, which is what this is, might as well just work in 3 dimensions. So the first thing to understand is that, and we saw this in Math 201, those of you who've done it, is that if you have something like this, ax plus by plus c is equal to whatever this number is, that's a plane. This is a plane, the variables are x, y, z. It's a plane in the x, y, z space with normal A, B, C. So it looks something like this. There's the normal A, B, C, or maybe it's pointing the other way, and this gives you some sort of plane. And now, when you assert several of these sorts of equations, now, then, let's say n equals 3. So if I have some number of these equations, what I'm doing is trying to find all the points that lie on all of these planes. You're looking at n different planes. So if I'm in an n by 3 matrix case, maybe an augmented case, so n by 3 plus 1. What I'm looking at is n different planes. So what are all the points on all the planes? So if 2 of the planes are parallel, then there's going to be no solutions at all. If there are only 2 planes and they intersect, there could be infinitely many solutions which lie on the line. But if there's 3 planes, then they could just intersect at a point. If there's 4 planes, they might also intersect at a point. Or if the new plane doesn't go through the point, there might be no solutions. Okay, so there's going to be some relationship between the number of solutions and the geometry of the thing. Because we're dealing with more than 3 dimensions most of the time, a lot of the time, it's not always going to be possible to draw what we're doing. But it's good to have an intuitive idea that what we're really doing is looking at intersections of planes or hyperplanes of high dimensions. A question? Yeah, I just meant that I'm adding an augmented column there so that, this would be A, D, C, capital C for this one equation. And then, of course, you have other equations, and for each equation, you fill it in. So it'll be a 4 by n matrix. But the interpretation, since we've got the vertical line, is that the coefficient part of the matrix is 3 by, or n by 3. So there's n 3-dimensional objects. And then the 1 just tells you that the capital C controls not the direction of the plane, but where it is. As you change, little a, b, c is the direction of the normal, and capital C controls how far up or down it is, on that direction. Okay, so that's what I meant, 3 plus 1. So we'll look like 4, the line distinguishes between the coefficients and the right-hand side of the equation of constants. Okay, alright, well that's just a little bit of an introduction following 1.1. The question is how we're going to solve these matrices. And there's a technique called Gauss-Jordan elimination. Now, the entire section 1 much faster than you, it can do it much faster than me. But like a lot of things, it's useful to just know the algorithm. If you happen to have to solve a whole lot of linear equations, you probably want to use a computer in the end. Okay, but Gauss managed to do huge matrix reductions to solve astronomical problems without computers. So, along the lines of Taylor series and all that other stuff, we ought to know how to do it. So here it is. The idea is to reduce the matrix to an equivalent form. Alright, now, there's certain things you can do with equations. You can divide them by constants. If you have 2 equations that are true, you can add them together, you can subtract them, you can multiply 1 by 3 and then subtract it. This is all stuff that you learned in high school, solving sort of baby simultaneous equations, 2 variables, that sort of stuff. For many variables, it's not so easy. So I need to go over the algorithm of how to do it. And it's presented very clearly in the book. It's not particularly exciting, but you need to practice. You need to practice. It's not really understanding what you're doing. So, in order to sort of, I'll just present the algorithm. I can see that in class, you can read it in the book. I'll present it, and I'll just do a couple of examples and see what's going on. Okay, so you're starting with some matrix, and let's say it's augmented. If it's not augmented, the same trick still works. You just do it as if it were not, as if it were augmented, or vice versa. The line makes no difference to this. So that's the first thing I want to say. If you're eliminating just the coefficients, it's basically the same. Okay, but for this example, I'll always put an augmentation in there against the column on the right. Okay, so the first thing is, and they use the term cursor. Okay, by the way, this is called Gauss-Jordan elimination. It's sometimes known as Gaussian elimination, or at least it is in Australia. So if I should call it Gaussian elimination, just pretend I said Gauss-Jordan. Maybe Jordan's first name is Ian. Well, I was worth a try. I doubt it. It's true. Actually, I have no idea what his first name is. Alright, so basically what we're going to do is reduce this matrix to what is called an RREF, reduced row echelon form. It has a particular form, and I'll talk about that in a second. Okay, so the algorithm says the following. There's your old matrix. What you're going to do is pick a cursor. Okay, I've never heard that term before used in this, but, it's a computer term, I guess. We're just looking for where to start. We're going to mark that thing. So basically, the cursor is normally going to start here in the top left corner, but that could fail when you have a column of all zeros. So actually what you want to do is sort of skip those. They're sort of irrelevant. That would be like saying 0x. If there's 0x, because there's 0x, x doesn't come into it in any of the equations. So that variable is sort of dead. It can be whatever it likes. It doesn't affect anything. So we want to do all those rows. So the step 0 is not explicitly said. It's sort of at the top of the algorithm in the book, but it's just like cursor is basically the top left, or the top entry of the first non-zero column. you sort of ignore the columns at the beginning, they're all zeros, and find there's your cursor. Okay, these are all zeros, then there's something non-zero. Of course, if the whole matrix is zero, well, then you don't really have any equations at all. Like 0x equals 0y equals 0z equals 0. Well, yeah, that's true for any x, y, z, whatever. So hopefully there's a non-zero row, or column rather, and so the cursor you're going to put at the beginning. Okay, fine. Now, you also don't like a zero at the cursor position, so what you have to do is you work your way down until you find that first element. Okay, so 0 is the preparatory step. So step 1 is that you want to find for the first non-zero row, or non-zero element, by working down, and swap the row up to the first row. Okay, so let's just look at what, in the first is just to pick a cursor, that does nothing. What does swapping these two things do? Well, in terms of these equations, if you transpose two of the rows, or when I say swap, I mean you can either swap or you can just bring it up and shut the other one down. All we're doing is writing these equations in a different order. That corresponds. If necessary, write them in a different order. Well, that doesn't do anything, right? It's just, we haven't even manipulated them, we've just written them down in a different order, right? X plus y equals 2, x minus y equals 3. That's the same as x minus y equals 3, x plus y equals 2. It's really a no-brainer. Okay, so now we can guarantee after step 1 that, okay, the 0 is here, but the non-zero has now been moved to the top, or whatever else it is. Okay, so the next step is sort of specific genius step. So divide, we're going to divide the top row, or divide the cursor row. So the cursor is still here, that focus. We just switch the rows around. The cursor is here. Divide the cursor row by the non-zero number. Remember, and the cursor. So when I say divide the row, I mean we're going to divide every number in the row, including the augmentation. Okay, so in the equation, what we've done is divide this equation by one of the numbers, by one of the coefficients. And of course, that's an acceptable operation. You're allowed to divide an equation by a number. So we're changing the coefficient, sure, but we're still remaining consistent with the original equation. We're not changing the equation as such. We're not changing the solutions to the equations. We're changing the equations. Anyway, step 3, now you have a 1 here. Whatever this is, you've now got a 1, because you've divided it by whatever the non-zero is, and that's not enough. Okay, so now you have to find every other row in the entire picture. In the entire matrix, what you have to do is subtract a multiple of this specific row to get zeros in a cursor column. So subtract a multiple of that cursor row to make all of the rest of the column. Where the cursor is, the cursor column. 0. And you can do that, no matter what the coefficients are. Like if the coefficient here is 3, you subtract 3 times this row from here, and that will knock you out the 3. If it's a minus 1, you add 1 times the row, so subtracting minus 1 at the same time as adding 1. So you can clearly do that, and you can knock everything down to 0. Now why is that acceptable? Well, again, all we're doing is adding a multiple of one equation to another. We decided that was allowed. No problem. It's 3 times that plus that is also true. Question. Why is that still true? It's not augmented matrix. Well, if it's not an augmented matrix, it's a question of what you're actually doing. Right? Now, if it's not an augmented matrix, you may as well assume that it is with all zeros in a row. What you're really doing is manipulating the coefficients. But you are changing the geometry of the situation, no doubt about it. Right? I mean, it's not the same point, but you will still get the same intersection point if you put any augmentation and respect the operations. Now, when I say respect the operations, I mean, you cannot just do this. Take this, it's augmented. Ignore the augmentation, do the elimination, and then stick the augmentation back. That's not allowed. The augmentation has to go along. The one little case is that if the augmentation was all 0, namely the right-hand side of all these points is 0, then it is respected. None of these things affect the 0. Okay, so if it's not augmented, you might as well think of it as augmented with a 0. Okay? That's just a matter of philosophy. Another question.
General question.
Yeah.
Why are lines important?
Why are lines important? Okay, the reason that lines are important is that really it comes down to A, they are the simplest geometric objects, but moreover B, it's really to do with linear transformations. So the lines are preserved by linear transformations. Now we haven't done them yet, but I'm hoping to do them. Well, you've probably started with the class. Now, I'm going to define a linear transformation later on, but let me just say the things that are not even in this course that you have seen are linear. Just for the purposes of now, let's just, the baby definition is that if you have two objects and you can add them together, then if I transform both those objects and add them together, it's the same thing as if I added them together first and then transform. Okay? Now you've seen something like this. You can take two functions and add them together and get a new function, such as x squared plus x cubed. Now these aren't linear functions in x, but if you think of this as the sum of two functions and then you differentiate them individually, the derivative of this is 2x and the derivative of this is 3x. right? So the derivative of the whole thing is, in fact, 2x plus 3x squared. So what I'm trying to say is differentiation is a linear operation on functions. Even though you don't think of functions as vectors, if you do, then the derivative is a linear operation. There's just many things that are linear, meaning that, again, they preserve the sufficient. They also have to preserve scale multiplication. There's many things that are finite dimensional, which are linear. And so part of the objective of this course is to study not just plain also integrate the sum of two functions. That's the same thing as summing up the integrals. Okay, so there's just so many things that are linear, and they're easy to deal with. In fact, you'll hear someone say, oh, chaos theory, that's all about non-linear. And it is. And fractals and all this sort of chaos stuff that was big, fly effects, that's all non-linear. Butterfly effects, you heard of this, right? This is where, butterfly claps its wings and then generates a hurricane by something, a few months later somewhere else in the world, just because of this sort of cascading effect. Well, if it was linear, then a small thing here would produce a small thing there, or at least if you double something here, you double it over here.
At low temperature, the volume fraction is 1. The volume fraction stays very close to the temperature, and then at some point it drops to 0 in SPC. There are many data points here. It's hard to tell whether it does that continuously or discontinuously, but in any case, it's roughly a box function. Okay, so the volume fraction is 1, and then it drops to 0. Now, let's go to 9.6 kilobars. So in the phase diagram, the tri-critical pressure is at roughly 12 kilobars. So the light blue curve is at 9.6, so that's somewhere here. Okay. And you see it still does essentially the same thing. It goes to 0 a bit more gradually. Now you actually have data points in here. So that going to 0 is a bit smeared out. But the important point that I want to make right now is that at low temperatures, the volume fraction is still equal to 1. And now we get to 11.7 kilobars, which is right around here. Okay, it's close to the critical pressure. And now you see what happens is that even at 0 temperature, the volume fraction is no longer 1. And as we go to higher pressure, fortunately my pointer is dying, probably the batteries are getting weak. I think I lost it. Do we have a laser pointer I could use? It's not a big deal, I can do without. So if you look at the light green curve, that's around here, and you see even at 0 temperature, it's still there, but it's weak. Yes. Oh, good. Thank you. Oh, this is yours and this is mine. So yes, it's a red one. Okay. So here you see it's even at 0 temperature, the volume fraction is less than 1. Okay, so somehow 20% of the stuff at this point is not magnetically ordered, 20 volume percent. And if you go to 12.9 kilobars, which is somewhere here, you see it's only about half of the material, volume-wise, that's magnetically ordered, and then it loses it altogether. So these are very interesting experiments for a whole variety of reasons. And if my time schedule works out as intended, then I will come back to these observations in the last lecture. For now, let me just say that the muon spin rotation community considers this kind of observation as a primary indication that the nearby phase transition is first order. So a phase separation of some sort, and that's characteristic of first order transition. There are very interesting questions to be asked, which again I may or may not have time to come back to. So let's just take that observation now for now as an indication of a first order transition. That doesn't come isolated. There are a lot of other observations that indicate that the transition is first order. Actually, the first suggestion was via diffusion measurements by Gilon Dulwich and Christian Kleider, I think, in 1997. Okay. So here are two examples of the transitions that are first order. And now I need... yes. So, here is another one of these materials. My laser pointer has been covered. Okay. This is uranium germanium 2. So very different material. You see here we have transition metal compounds. And by the way, they are all metals. Okay, so all the materials I'm going to talk about are metals. So here's uranium germanium 2. At ambient pressure, the Curie temperature is 47, 48 Kelvin, depends on the sample. It's again pressure dependent. Curie temperature marches down as you increase the pressure. So that's a temperature, pressure, magnetic field phase diagram. And here is the tri-critical point. So as we go below this temperature via pressure, the transition becomes first order. And if one now turns on a magnetic field, Then what happens is that the phase diagram develops this interesting ring structure. So out of the tricyclical points come lines of second-order transitions that eliminate surfaces of third-order transitions. So here the light crystalline blue surface is of course a first-order transition from a spin-polarized paramagnet to a spin-polarized paramagnet this way. And here you have these surfaces, and the meaning is that as you cross any of these surfaces,